In this video we're going to investigate electromagnetic radiation, or EMR. But before we do that, let's just briefly revise what we've already learned about waves. We have learned that waves are repetitive disturbances of a medium, and that waves have a wavelength lambda, and the amount of waves that pass a point in a medium per second is known as the frequency, and that these are related as follows to produce the speed of the wave in the medium. This is known as the wave equation, the classical wave equation. So V represents the velocity in meters per second. The frequency is measured in hertz, which is equivalent to seconds to the -1 or per second, and the wavelength is measured in meters. We used the formula triangle as follows. V in meters per second is the frequency in hertz times the wavelength in meters This is a very useful equation which we are going to use when looking at electromagnetic radiation. It's also useful to remember that the period, which is the amount of time that it takes for one wave to pass a point in the medium, is 1 over the frequency and is measured in seconds. So the period is 1 over the frequency in hertz, period in seconds, and thus the frequency is also 1 over the period. So electromagnetic radiation, or EMR, is an umbrella term for a wide variety of different types of radiation that we have come across. So first and foremost, visible light, which includes red, orange, yellow, green, blue, indigo and violet, is part of the electromagnetic spectrum, but only a very, very small part of the electromagnetic spectrum. If we see here that red light ranges from about 700 nanometers, or 10 times 10 to the -9 meters, to violet light, which is approximately 400 times 10 to the -9 meters. The electromagnetic spectrum also includes radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays and gamma rays. And albeit that all of these types of radiation we view as being different, in essence they are all one and the same thing. The only thing that really differs is the wavelength, and hence the frequency of that particular radiation. If you have not done so already, I strongly encourage you to look at the YouTube video clips that I have referred to on our Pi page. You will find that these video clips give you a deeper insight into electromagnetic radiation and what causes it. In short, electromagnetic waves are created by accelerating charges, which result in rapidly changing magnetic and electric fields. So if this is the source of the electromagnetic radiation here, there would be an accelerating charge. It could be accelerating in 3 dimensions, and what it does is it results in a varying electric field, which in turn induces or creates a varying magnetic field. Now later on in your studies in physics you will learn about electromagnetic induction, where a changing electric field induces a changing magnetic field, but a changing magnetic field in turn induces a changing electric field or varying electric field. So this is a self-propelling or self-perpetuating wave which can move through space indefinitely. As we see in the universe, when we look up at a night sky, the light that we see from the stars have been traveling for millions and sometimes billions of years to reach us, and they've been traveling through mostly vacuum. Now, what's very important about electromagnetic radiation is that because it is not a normal wave, but where there's a variance in the medium or disturbance in the medium, but rather a varying electric and magnetic field which are at 90 degrees to each other, the EMR does not actually need a medium. So electromagnetic radiation does not equal a mechanical wave. So it's very different to anything that we have experienced up to this point. There's also another very important characteristic of electromagnetic radiation, and that is that the velocity of electromagnetic radiation is equal to 3 times 10 to the 8 meters per second, which is commonly known as the speed of light. Now, the speed of light is a constant in a particular medium. So in vacuum, the speed of light is 3 times 10 to the 8 meters per second, which is 300,000 kilometers per second. Now that is extremely fast. No matter can travel faster than the speed according to Einstein's theory of relativity. To give you an idea of how fast this is, the circumference of the Earth is approximately 40,000 kilometers. So traveling at 300,000 kilometers per second, light can circle the Earth 7.5 times in 1 second. So this is an extremely fast speed. If the density of the medium increases, so for instance if light or electromagnetic radiation travels through glass, then there will be a significant drop in this velocity. So in the case of glass it drops to about 200,000 kilometers per second, but I'm sure you'll agree with me that that is still exceptionally fast. Now, using the velocity formula of v equals frequency times lambda, as we referred to at the beginning of this video, and taking into consideration that electromagnetic radiation travels at the speed of light, and the symbol for the speed of light is c, we now can rewrite this as c equals frequency times lambda. But I want to emphasize we only use this form when we are dealing with electromagnetic radiation. And we will be using the value of 3 times 10 to the 8 meters per second for the speed of light. We can adjust our formula triangle now as follows. We can write c as frequency times lambda. Remember, c is now 3 times 10 to the 8 meters per second. Lambda is in meters and frequency is in hertz. So the concept of a spectrum is that there is a continuous range of a particular thing. So if we think, for instance, of the rainbow, you can think of that as a spectrum of visible light. We've got red, orange, yellow, green, blue, indigo, violet, where they flow into each other. Now the electromagnetic spectrum is also a wide range of wavelengths and frequencies that range from the extremely small wavelengths to the extremely huge wavelengths. And it's a continuous spectrum, so we have an infinite amount of frequencies and wavelengths in this particular spectrum. So let's look at wavelength. So if we write lambda here, we'll see that with gamma radiation, which is caused by the disturbances or in the nucleus of protons, where we have accelerating charge within the nucleus, we get extremely small wavelengths, and then as we move through X-rays, ultraviolet, light, infrared, microwaves, TV signals, radio waves, moving down like this, what we find is that the wavelength increases. So the wavelength increases going from gamma radiation all the way through to radio waves. So radio waves can be tens of meters, hundreds of meters, even kilometers long, whereas gamma radiation is of the order of 10 to the minus 14 meters. Now, that is extremely small. That is smaller than the diameter of atoms, and that is one of the reasons why it is so dangerous, is because it has the ability to actually knock protons out of the nucleus of atoms. 10 to the minus 14 meters is of the order of the diameter of a nucleus. And so, for instance, in nuclear explosions, the radioactivity produced, gamma radiation, has the ability to interfere with the protons and the neutrons and actually to change the composition of the nucleus. And this results in changing what they call base pairs in DNA, and then this can result in genetic mutations and all sorts of negative effects in the children of people who've been exposed to gamma radiation. So if we look at frequency, now remember frequency is going to equal C over lambda. So frequency is inversely proportional to lambda. Then gamma rays have an extremely high frequency, and then as we move down, the frequency decreases until radio waves, which have a very, very low frequency. So going from gamma rays down to radio waves, the frequency decreases. In grade 12, we are going to focus more on the energy of electromagnetic radiation when we deal with an effect called the photoelectric effect. But for now, if you can just remember that the energy of electromagnetic radiation is directly proportional to the frequency, and therefore the energy will decrease as one moves from gamma radiation down to radio waves. For our grade 10 syllabus, it's important that you are able to complete a diagram like this, where you would be asked to fill in the types of electromagnetic radiation, where the wavelength starts, for instance, very big, and then decreases to where it is very, very small, and where the frequency would be very small, and moving through the spectrum to where the frequency would be very large. So yeah, at the bottom of this particular diagram, your frequency would be increasing, and at the top of the diagram, your wavelength would be decreasing. Now, this diagram is not drawn to scale, because there are many orders of magnitude. By that I mean by timesing by 10 or dividing by 10, that these wavelengths and frequencies range through. But these kind of diagrams will be given to you, and there will be certain types of EMR that will be placed in these diagrams, and then you will have to fill the open spaces. But if we look at this open diagram here, we're going to work through it, and we are going to place the types of electromagnetic radiation into the diagram. So starting on the left hand side, the type of radiation that has very long wavelengths and tiny frequencies is radio waves. So I'm going to use the symbol RW, the abbreviation RW for radio waves. Then from radio waves we move to microwaves, and we know that microwaves are it's the range of electromagnetic radiation that we find in microwave ovens, and that's around about the millimeter centimeter range. It's good to know this is around about millimeters and centimeters, whereas radio waves can be kilometers and meters. Then moving to the right, after microwaves we have infrared, and then we have the visible spectrum. Now the visible spectrum is what we call light, and it runs from red to orange to yellow to green to blue to indigo to violet. So to the right of visible light we will then find ultraviolet light. And ultraviolet light is the form of electromagnetic radiation which makes, if we go out to the beach, that turns our skins darker. It affects the melanin that is a pigment in our skin. So when we say we've been sunburnt, we've actually been ultravioleted, if you want to call it that. Then after ultraviolet radiation we have X-rays, and we all know about X-rays. When we break a bone or fracture a bone, we go to the hospital, they use an X-ray machine to see whether the bones have been broken. And then something that we don't, unfortunately we don't have dealings with on a daily basis, is what we call gamma radiation. We use the Greek letter gamma, which is this letter here. That is gamma radiation. Now, if we look at keeping in mind that energy is proportional to frequency, then the energy of radio waves is very small. And as we move from radio waves to microwaves to infrared to visible light to ultraviolet to X-rays to gamma rays, together with the frequency, the energy of EMR also increases. And hence X-rays and gamma rays have very high energy values, and therefore are able to penetrate deeply. So this is why one has to be careful when you get X-rayed, that you don't get X-rayed too frequently. And with gamma radiation, as I've already mentioned, gamma rays can penetrate very deeply, deep down into the nucleus of our atoms. So this is a really important diagram for you to remember and to learn when preparing for tests and examination questions on electromagnetic radiation. So let's now look at a numerical problem pertaining to electromagnetic radiation. So up in Johannesburg there is a radio station that they call 94.7 Highveld stereo. Down here we have 94.5 KFM. Now the 94.7 uses radio waves of a frequency of 94.7 megahertz. Now it's really important to remember what the prefixes in physics mean? So when we talk about, we'll refer to prefixes, when we talk about kilo, we are referring to times 10 to the 3 or times 1,000. So for instance, 1 kilometer is 1,000 meters. Mega is referring to times 10 to the 6. Now when we talk about prefixes, pre means before. So it's what we put before a unit. So megahertz, it's pre before the unit. So that in actual fact means times 10 to the 6 hertz. And then if we refer to giga, giga is a billion, which is times 10 to the 9. And we know that nowadays with, when we talk about computers, we talk about gigabits and gigabytes and gigahertz. So that is a billion. And then tera is times 10 to the 12, and that is a trillion. So a lot of radio stations broadcast using radio waves of several million hertz. So the question here asks, how many times a second does an electron in the radio broadcasting antenna move up and down the antenna for 94.7 megahertz? So you've done a fair amount of calculations on waves. So I would like to encourage you to pause the video here and to give this one a try. So going back to the definition of frequency, which is the number of vibrations per unit time, or the number of waves that passes a point per unit time, and keeping in mind that hertz is the same as per second, the answer to the first question is, if the frequency is 94.7 times 10 to the 6 hertz, then how many times does an electron in the antenna move up and down the antenna per second? And it's 94.7 million times per second, which we know is a large number. Let's look at the second question. So what is the wavelength of the radio signal sent out by this radio station? And yeah, again, I would like you to give this one a try on your own. So pause the video and please try and get the answer, work out the answer to this question. So because radio waves are electromagnetic radiation, the equation C equals F times lambda is valid. C is the speed of light, but also the speed of radio waves. We're assuming that the speed of light in vacuum and the speed of light in air don't vary by very much. There's a slight variance, but we are going to assume that the speed of light in air is also 3 times 10 to the 8 meters per second. So substituting for the frequency, 94.7 times 10 to the 6 hertz, and then dividing by 94.7 times 10 to the 6 in solving for lambda, we get that the wavelength of the radio waves that this particular radio station uses as their base signal, that's their fundamental signal, is approximately 3,17 meters. So now I challenge you to work out the wavelength for the radio wave, the base signal for KFM, which is 94.5 megahertz. So the frequency for KFM's base signal is 94.5 megahertz, which is the same as 94.5 times 10 to the 6 hertz. Because radio waves are electromagnetic radiation, it implies that the wavelength, the speed of radio waves is the speed of light, and that's going to equal the frequency times the wavelength for the radio waves that KFM uses. We can rearrange this formula by dividing by the frequency, and we find that the wavelength is equal to the speed of light divided by the frequency. So the wavelength is 3 times 10 to the 8 meters per second. We divide this by the frequency, 94.5 times 10 to the 6 hertz, and we find that the answer is 3,17 meters. Now you'll note that this is the same answer as for the previous radio station, but what we need to take into account is that there are rounding off errors here, and that 94.5 and 94.7 are quite close to each other, albeit that they are megahertz. And because we are working out these answers only to 2 decimal places, that the actual variation in the wavelengths between these 2 radio stations actually lies in the 3rd and 4th decimal place. But the method, as you can see, is exactly the same. And now what I would like to ask you is to work out how long it takes for the electrons that are accelerating, causing these radio waves in the antenna of KFM. How long, time-wise, does it take for these electrons to complete one vibration? So pause the video and try and solve the problem that I have put forward to you. Using the fact that the period is 1 over the frequency, we can now work out what the time is that it takes for one full vibration. So 1 divided by 94.5 times 10 to the 6 hertz gives us an answer of 1,058 times 10 to the minus 8 seconds. So we can round that off to 2 decimal places. And as you can see, that is an extremely small period of time. So the following questions will also be placed on Google Classroom, and this is your homework on this section. So I encourage you to do this in your own time, and at a later date the solutions will be posted. But please note that the answers to some of these problems are given on the right hand side here, and then please ensure that with every single one of these problems that you put down the formula, show the substitution explicitly, and then write down the answer with the correct unit. This is also an interesting question which I would like you to attempt. Explain why ultrasound is used to monitor the development of babies instead of X-rays. Please describe the differences between the 2 types of waves and give scientific reasons for your answer. So I hope that this video has helped you to take what you learnt in the sections on waves and sound to apply it now to electromagnetic radiation.